Okay, our last section in Unit 8 says buffer capacity. We've already talked about buffers. We're going to kind of catch a lot of the things we've done in Unit 8, and this is going to be more of a practice session and kind of encompass as many different concepts as we can here. So no new information, just practicing really. So our first question doesn't even deal with acid bases per se. It's Lewis dot structures. It says complete the Lewis electron dot structure of HNO2 in the box below. Include any lone pairs. So I think you guys know that you need two dots between hydrogen and whatever else it's with. Typically nitrogen has a lone pair. Typically oxygen has two lone pairs. Well, we need 8 electrons around every atom other than hydrogen. So the hydrogen looks good. The first oxygen on the left hand side looks good. The nitrogen and the oxygens do not look like they're complete yet octet wise. If we give it a double bond there, but by the way, I think you could get away with lines instead of dots there. We'll double check answers in a little bit here. Based on the completed diagram above, identify the hybridization on the nitrogen atom. I'm going to kind of move nitrogen over here. We have that, we have that, and we have that. That looks to be like 3 domains, which is sp2. Move this up a little bit. Okay, what do we got here? Part E. So we have, looks like 4 lines of words. We have a chemical reaction. This is a titration. So we have a weak acid, HA, and a strong base, OH minus, making A minus, okay. And this would be our equivalence point. This would be our halfway point. This would be our initial point. And somewhere out here, we'll be approaching our maximum amount of potassium hydroxide, which should give us our maximum pH. I'm not sure what all we need with that. Let me erase these so we can also talk about what's in here. We have a 100 milliliter sample. We have a 0.1 molar KOH solution. It says determine the initial concentration. So I think this looks to be like some factor label. It's all 1 to 1 to 1 here. So 1 mole of HA, not A, HA is equivalent to 1 mole of hydroxide. We have a 0.1 molar hydroxide solution, and it says initial concentration. It took us 20 milliliters to neutralize that. So that's, even though it doesn't mention anything about the equivalence point, we have to know that that's the equivalence point. And then we were given a 100 milliliter sample, which is 0.1 liters. So do that math, and we get, that looks like a 6. We don't want a 6 there. .02 molar. Estimate the pKa. Well, looks like it was important that I figured out the halfway point, because remember at the halfway point, pH equals pKa. And why is that? Because the A minus and the HA are in equal amounts. So divide those two things, you get 1. Log of 1 is 0, so that just wipes all that out. So we're going to have to estimate it here. It's a little hard to see exactly, but it's a little over 3. I would say maybe somewhere in the 3.3 range. Difficult to say, and there's a little leeway there, I'm sure. You couldn't get away with 4.3, I know that, but 3.3 should be fine. In part F, during the titration, after a volume of 15 milliliters of 0.1 molar KOH has been added, which species do you have more of? So let's go back and talk about these points. So at the halfway point, you have equal amounts, equal concentrations of those two items. Before that, you're going to have more of that initial compound, and then after that, you're going to have more of the product, in this case NO2 minus. So I think we might have just answered that question. Here's all the work. You guys can check that out on your own. They said 3.4, I said 3.3. Okay. Question number 2. Let's see here. We got a Ka and we have a pKa. That was nice, so we don't have to worry about that. We want to make a buffer with 3.4. So it looks like our pH and pKa are going to be identical. So that means our A minus and HA are also identical. But here's the thing. We have to make it with those two chemicals. Explain why the addition of 0.1 molar sodium hydroxide to 0.1 molar HNO2 can result in the formation of a buffer. So that looks like, well, how can I make a buffer with those two things? Well, you can. So let's add it up here. So HNO2 and sodium hydroxide make H2O, which doesn't help out our buffer, but it also makes NO2 minus. So if we have HNO2 left over and we make NO2 minus, we have a perfect buffer. And it says determine the volume that you would need to make this buffer. Well, what we need to happen, and I'm just going to write over here, ICF, we need at the end of the day, in the F and in this F, we need the same amounts. We need all the hydroxide to run out. So let's see. Well, actually, it's hard for me to write over this work. So maybe we'll just go and look at, no, you know what? We will talk about this. So to make this so we have equal amounts of HNO2 and NO2 minus, we need to get to half. Let's go back. So when we were looking at this is a different question, but the same idea. To get to the halfway point, you have to get halfway. So, whoops. If you're using 100 milliliters of the HNO2, I think we should probably use half of that volume, and that would get us right there. Let's double check those answers for part C. Okay, so there is our net ionic. We like that. And there's our 50 milliliters I mentioned. And so if you had 50 milliliters, those two amounts would be identical, and the pH would equal pKa. Let's jump back and see what's going on with D here. A second student makes a buffer by dissolving 0.1 moles and 100 milliliters in 1 molar of that chemical. which is more resistant to changes in pH? Whichever one has more moles. And I believe this is going to give us more moles, the second students, as opposed to the first student. So if you would try to, if you would get those milliliters with that molarity, I think you would find that we're going to have, the second student's going to have a greater number of moles. Double check our answer here. Seconds. The buffer made by the second student is more resistant because it has higher concentration. Yeah. Oops. And we have a part E here. New buffer. It's in a particle diagram. Is the pH of this buffer greater than, less than, or equal to 3.4? So we have pH equals pKa plus log of NO2 minus, and then HNO2 on the bottom. So whichever one we have more of, that's going to impact our pH. We have 1, 2, 3, 4, 5 of the NO2s. And the HNO2s, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that equals 0.5. So what's going to happen is if you take the log of 0.5, that's going to give you a negative number. So that pH is end up going to go lower. Double check. And they actually did the math of it too. I don't think we had to do the math, but they got a pH of 3.10. Get a couple more questions. Okay, we have phenol. So that could be our HA. And here is our A minus, and we have a Ka. It says, what's the pH of a 0.75 molar solution? So Ka equals x squared up top, 0.75 on the bottom. Solve for x, that's hydronium, and then you can get pH from that. And we'll check out some answers. And 5.04. Remember that we've been making that assumption over and over and over again. If we look at that x value, it certainly does not impact 0.75, so we were able to do that. Part B, let's see here. For certain reaction involving the phenol must be primarily in its deprotonated form. It defines what that is. So that is in its A minus form. On the number scale below, circle each pH for which more than 50% of the phenol molecules are in the deprotonated form, meaning that this is greater than this. So if you have that situation, when you take the log of that, it's going to give you a negative value, and that's going to make that's definitely going to impact the pH. Okay. Oh, I'm sorry. The A minus is going to be greater. That will not make that'll make a positive pH. I'm sorry about that. So that's going to increase the pH. So what was our pKa? It didn't actually calculate the pKa of that, but when you do the log of that, you're going to get 9.95 for the pKa. So we're looking for anything going to be above that number. So I guess all those would be okay. 10 is barely over 9.95, but it's over 9.95. Can double check those answers. Yep, that's good. And our last question, We have potassium sorbate added to soft drinks as a preservative. We have a stock solution with a known concentration. Student titrates 45 milliliters of that stock solution with 1.25 molar hydrochloric acid. I guess we need a net ionic. Hydrochloric acid is a strong acid. And then potassium and the sorbate, they're going to break up. And so you're going to get that. And we'll just combine those. I think that's a pretty good net ionic. We have a volume and molarity to reach the equivalence point. And remember, we were also told we had 45 milliliters of the stock. So you could get away with doing an M1V1 equals M2V2, or you could do factor label. Either of those would be terrific. I'm not going to do either because we can just check out some answers. So they didn't do the M1V1, which you're not really supposed to do. They did their factor label in 2 steps. I would have probably preferred doing that all in 1 step myself, but there's your answer. Okay. It's a 1-to-1 ratio between the 2 components there. Looked like that net ionic was good. Let's go back. Okay, so the pH of the equivalence point is 2.54. So what kind of indicator should we use? We should use one that has a pKa close to that. And I think the closest we're going to get is going to be thymal blue. Justify your answer. I think that's going to be just enough justification that you're going to get the color change occurring closest when the pH equals the pKa of the indicator. Let's see what they say. Yeah. And then let's go to part D. Calculate the pH at half equivalence point. Remember, half equivalence point, you have this happen. pH equals pKa. And we already have a pH. Wait a minute. That's at the equivalence point, so that's not going to help us out. I was almost going to write that down. We have a Ka, so take the negative log of that. So the pKa is 4.77. Okay. Part E, well, let's double check before we move on. 4.77 it is. Okay, so let's go back to our question. So we have a graph this time. The initial pH, so that was dotted on here. I'm going to make the dot just a little bit more dramatic there. We have another dot here. Accurately sketch the titration curve on the graph below. Well, we have the equivalence, we have the halfway point. So if the equivalence point was 30 milliliters, the halfway point would be 15 milliliters, and then we know it has to be 4.77. So there's 5 there, so that has to be just a tad under that. That looks like a straight line to me and you, but we need the following to occur, if you remember. So at the equivalence point, we'd like that to happen. At the halfway point, we'd like to have it be fairly horizontal. And now we can try to connect these as best we can. And I don't remember what the initial, what the pH of the acid was, so I don't know where that's going to lead us. I might have just been a little bit off on that. But there's a lot of leeway here. but you needed a couple of those things to occur like I just showed. So let's check out to see what they liked. Oh, you know what? I was supposed to also put an X. I'm sorry. At the halfway point, I put a dot, but not an X. Sorry. So they have a, kind of a horizontal there, kind of a vertical there. It dips early on and then starts to flatten out as you get into the buffer range. Okay. And that might have been, it might have been our last question. It wasn't. pH of the soft drink is 3.37 after the addition of the salt here. Which species has a higher concentration in there? So pH equals pKa plus log of A minus over HA. pH 3.37. The pKa was 4.77. So for that to happen, this whole thing has to, this log of A minus over HA has to be negative. And the only way that's going to happen is if our HAs are more than our A minuses. And that's it. That concludes Unit 8.